Welcome back. The best way to grasp how machines capture and process speech is to understand how humans do it. After all, this technology's development is primarily inspired by the way our bodies react to sounds and speech. Hearing is vital. It allows us to communicate, enjoy surrounding sounds, and connect with the world in fascinating ways. Just like machines, our brains interpret sounds as electrical signals generated from sound waves. That's right. Our brains capture and process electrical signals to understand sounds. Let's see how that goes. Sound originates from a source emitting waves, characterized by frequency, the number of vibrations per second measured in hertz, named in honor of the German physicist Heinrich Hertz. Higher frequencies produce higher pitches, whereas lower frequencies yield deeper sounds. These waves enter the ear, traveling through the canal to the eardrum. The eardrum then vibrates at the same frequency as the incoming sound waves. For example, when a nearby pianist strikes the A4 note, also known as La, it emits a 440 Hz sound wave that makes your eardrum vibrate 440 times a second. Impressive. This occurs in both ears at once, enabling you to pinpoint the sound's origin by comparing the differences in signals received by the ear. How cool is that? Next, these vibrations are transmitted to tiny bones that amplify the sound vibrations and send them to the cochlea, a fluid-filled structure in the inner ear. Within the cochlea, microscopic hair cells respond to fluid waves by generating electrical signals transmitted to the auditory nerve. This nerve transforms the signals into neural impulses and conveys them to the brain, interpreting them as recognizable sounds. Wow! So this is how sound signals travel to our brains. How then do we identify the sounds? After several additional processing steps, the brain decodes the signal and determines various aspects of sound, including pitch, volume, and duration. A part of the brain called the auditory cortex analyzes these elements to recognize patterns such as speech, music, or other familiar sounds. Does that sound familiar? If you recall prior lessons, pattern recognition fundamentally supported initial speech recognition experiments with strikingly similar mechanisms. Modern speech recognition mechanisms, however, use machine learning and neural networks trained on vast data sets of spoken language. Although they don't traditionally rely on stored patterns, they require extensive input data to learn how to recognize and interpret speech effectively. Great! We now know how we as humans hear and interpret sounds and process sound waves. In our next lesson, we'll explain sound waves in greater detail to improve your understanding of speech from an audio engineering perspective. See you there. Hi, are you ready to learn more essential audio knowledge? Let's begin this vital lesson by explaining the common physics term wave. A wave is a disturbance that transfers energy from one location to another through a medium or empty space. Waves vary by nature. Mechanical waves need a medium composed of particles, such as air or water, to travel. Sound waves are a mechanical type. Conversely, electromagnetic waves like light travel through space without a medium, allowing sunlight to reach Earth through the vacuum of space. So why does sound need particles to travel? Well, sound waves need particles in a medium, such as air, water, or solid, to carry vibrations from one location to another. Without particles, these waves cannot travel. When a sound wave travels, it causes the medium's particles to vibrate back and forth, with each particle passing its energy to adjacent ones, initiating their vibration. The process continues with each particle transferring energy to the next, creating a wave of vibrations that spread through the medium. And this is how sound waves transfer mechanical energy. Particles, however, don't actually travel with the wave over long distances. Instead, the wave's energy moves through the medium. Imagine a row of people standing side by side. When one nudges another, the nudge travels down the line while each person remains stationary. Similarly, particles in a medium move slightly when a wave passes through them. Good. When we speak, our vocal cords create vibrations in the air. These vibrations cause nearby air molecules to bump into each other, transferring the sound wave's energy forward. The air molecules themselves don't travel from your mouth to someone else's ear. They just pass the vibration along, much like a domino effect. Let's clarify this further. When you observe water waves spreading across the sea, the wave's energy progresses, not the water itself moving across the sea. This is why a floating object like a buoy or a boat bobs up and down as waves pass. It doesn't get carried along with the wave but moves vertically, demonstrating the difference between energy and matter transfer. So let's summarize. Sound travels in a medium by causing the particles in this medium to vibrate. The effect is referred to as sound waves. Furthermore, as sound waves travel, they lose energy, spread out, and become less intense, gradually fading the sound until it disappears. For instance, when shouting across a large field, your voice begins loudly but fades and becomes more difficult to hear as the sound waves disperse and lose energy with distance. Imagine if sound waves never disappeared. Every sneeze would echo eternally. We'd all constantly say "bless you" to sneezes from 100 years ago. Alright, with that intriguing concept, we can conclude this lesson. In the next one, we'll continue the discussion on sound fundamentals by exploring the key properties of sound waves. See you soon. Hi there. Let's closely examine the fundamental properties of a wave and discuss how each one affects the sound we hear. We'll start with amplitude, one of the most fundamental characteristics of a sound wave. Amplitude represents the maximum displacement of particles from their resting position due to the wave's pressure. It relates directly to the loudness or volume of the sound. Larger displacements mean higher amplitude, resulting in louder sounds. While amplitude is technically a measure of distance, it's often expressed in decibels, a logarithmic unit that helps represent the wide range of human hearing on a manageable scale. Next, we have the wavelength, which is the physical distance between two consecutive points in the same phase of a wave, such as two peaks or two troughs. It's measured in meters, but don't confuse wavelengths with the literal length of a single wave. It's specifically the distance over which the wave's shape repeats. Closely related to wavelength is the period of a sound wave. This period is the time it takes for one complete wave cycle to pass a given point, measured in seconds. Unlike wavelength, a measure of distance, the period tells us about the timing of the wave's oscillation. Then there's frequency, which we've already mentioned several times in previous lessons and you're likely familiar with. Frequency, measured in hertz, indicates the number of complete vibrations or cycles per second and is inversely related to wavelength. Longer wavelengths correspond to lower frequencies and lower-pitched sounds. Low-frequency bass sounds have long wavelengths, allowing them to travel far distances and stay audible from afar. High-frequency sounds, which have shorter wavelengths, tend to interact more with particles and obstacles in the medium, losing energy more quickly. For instance, when you hear a high-pitched bird song, you can reasonably guess the bird is nearby, unlike the deep bass sounds you might hear from a distant concert. Lastly, let's discuss phase, which indicates the position of a point in time within a waveform cycle. Consider phase as a circular racetrack where a runner represents the wave. The starting line is 0 degrees. As the runner circles the track, halfway is 180 degrees, and a full lap returns them to the start at 360 degrees or 0 degrees. Just like tracking the runner's position on the track tells us how far they've gone, knowing the phase tells us where we are within the wave cycle at any given moment. Alright, we've covered some of the most essential characteristics of a sound wave. While there are other properties, these are the most relevant for understanding how speech recognition systems work. Let's explore why each characteristic is essential. Amplitudes reflect the loudness of a signal. Variations in amplitude help differentiate between phonemes and can indicate emphasis, which is critical for accurate speech recognition. especially in understanding stressed syllables or louder speech. Wavelength is closely related to frequency and helps us understand how sound waves travel and spread out in a physical space. Longer wavelengths can travel farther and are less affected by obstacles, while shorter wavelengths tend to be absorbed or scattered more easily. Period represents the time it takes for one complete cycle of the wave. This is crucial for analyzing the timing patterns of speech sounds, helping to segment speech into recognizable units like phonemes, syllables, or words. Frequency determines the pitch of a sound. Different phonemes have distinct frequency patterns, which are essential for distinguishing sounds and words in speech recognition systems. Phase information is crucial for understanding how different sound waves interact. It helps identify specific sound patterns and harmonics that contribute to recognizing different phonemes and speech nuances. When sound waves meet, they can interfere, creating new waveforms. This interaction can lead to constructive interference, with waves merging to amplify, or destructive interference, canceling each other. These interactions, influenced by phase differences or similarities, are fundamental to understanding wave behaviors like interference, refraction, and diffraction, which significantly affect the perception and behavior of sound. Great! Together, these properties help accurately capture and analyze speech characteristics, extract relevant audio features, and enable effective speech recognition. Before concluding this lesson, let's clarify something crucial. Although sound waves are commonly represented as sinusoidal time functions, this visualization is merely a mathematical model that aids in describing and predicting their behavior. They don't look like this, you know. A sinusoidal graph displays variations in pressure or particle displacement over time, illustrating properties like frequency, wavelength, amplitude, period, and phase. Great! We now understand sound waves and their essential characteristics. In the next lesson, we'll use this knowledge to reveal how sound waves are converted to a format that computers can understand. See you there.